Yes, great. So we were discussing this, and this was our second kinematical equation for constant A. We just integrated this. It looks very nasty, very nasty, but still we integrated it. Okay, so it looks something like this: A vector, not this color. It looks something like this. If you figure out, if you do sum of the algebra, it is minus t naught square by 2 plus t naught square. So it is plus t naught square by 2. And then this becomes a perfect square. Perfect square of what? T by root 2 whole square, t by root 2 minus t naught by root 2 whole square. So if you take root 2 common out, so it will be 1 by 2 a bar t minus t naught whole square. This will be the form. Can you see that form or not there? It will be, what will it be? It is t by root 2 whole square minus 2 times t by root 2 t naught by root 2 plus t naught by root 2 whole square, because this is this will make this sign plus, this will go away, and then it will become something like that. Can you see that or not? Or is it too hard to imagine right now? Okay, let me write a few steps.
Sir, like we can imagine, because if we put t naught equals to 0, we will get the initial equation what we used to work with, and we can clearly see that
Huh.
this represents that, like even if we translate in time, then it will represents the displacement what we need. If we it is
Yes.
like if it is given that the particle or anything is moving from 0 to t time, and we need the data of t naught to t time, so this equation will help directly to evaluate such thing. In case
Yes.
like if we look in another way, it just translate in time, this
Time.
equation.
Yes. This is the translation in time only, nothing else. Yes. So this is translation in time only, but from equation you should be able to see how did I wrote that equation. That is the only purpose. So this is equation number 1 for constant acceleration. This is ideally equation number 2 in vector notation for constant acceleration. And now if you actually focus on one dimension, then these equations becomes very simple. Focus on one dimension, then this becomes v only, this becomes v naught only, this becomes a only. If you focus for one dimension, then the life is very simple: v equal to v naught plus at. And for one dimension, if you put time t equal to 0 or t naught equal to 0, if you put time t naught equal to 0 for one dimension, these are the equations you started with. Okay, it is v equal to v naught plus at, where you need to keep in mind this equation. If you want to remember, you need to keep in mind that first step to use this equation is set up x-axis or any axis, y or z, whatever. For one dimension you need to set up one axis and then define positive side of the axis and negative side of the axis clearly. And then, since these are anyways vector equations, they are not scalar equations, so if you define negative and positive sides clearly, then use sign convention. This is the most important point. Okay, so you need to set up axis first, and then you need to define positive side of the axis, negative side of the axis. And if velocity is pointing out this, suppose this is your x-axis, this point is 0. Now this is your positive side by default, right side, and left side is negative side by default. You define it like this. That is your choice. Now if particle is initially moving in this direction, but after some time it reverses back and it is moving in this direction after time t. So t naught it is here, at time t it is here, t naught equal to 0 it was here. So v naught is negative in this case. V naught is negative in this case because it is pointing in negative x direction. Okay, that negative comes from the direction, not from the magnitude of v naught. That negative comes from the direction, and this is pointing in the positive direction. So it is, its value we take it as positive. Okay, so don't get confused between v naught is negative or the actual direction of v naught is in the negative x direction. The answer is actual direction of v naught is in the negative x direction. V naught is not negative. V naught is a magnitude of velocity, which is a speed by itself. But since this equation is a vector equation, we derived it from the vector equation. we put everything with a sign just to make sure that we are consistent on both sides. X cap cancels out on both sides. That is the reason. Okay, so ideally it should be vector, vector, vector here, but we write v vector now as some v times x cap. It is in positive x direction, and v naught as some minus v naught times x cap. Okay, and a is constant, so a is some constant times, in this case a will be in positive x cap direction, then only it can switch around. So these are the things that we already write there in this equation, but if we write it there, we just remove these vector signs because we don't need them. So we, instead of v naught, we put minus v naught, x cap we cancel out from both sides, or I should say in proper words, we just focus on magnitudes both sides because the unit vector is same on both sides. Okay, that's what we do. So don't get confused there that we are keeping these guys constant. So I should write this. Okay, don't get confused that why should we put them with the sign, because you set up the axis first and you decide which sign is it, because these equations are by its nature vector equations. They are not scalar equations. Okay. Yes. Second equation is very easy to write. For t not equal to 0, it is x equal to v0t. It is x naught plus v0t plus half at squared. Okay, you can see it here, v0t plus half at squared. That is your second equation. You can see it here. Wonderful equation this, wonderful equation that. And now if you want to derive the third equation,
Sir,
okay, if you want,
t
yes,
not equal to 0.
no, t naught is equal to 0. Because if t naught is 0, then only this equation t naught can go out, t naught
Yes, sir.
can go out,
Okay.
right?
Yes, sir.
Yes. Okay. And moving on to the third equation, which is only valid for one dimension. You will realize soon why. But third equation, which is only valid for one dimension, it is derived from this equation. V equal to v naught plus at, you know. Okay. So you just take square both sides. V square equal to v naught square plus 2at v naught plus a square t square. And if you see that it is v naught square plus, if you take 2a common out from both of them, 2a common out, then whatever remains, it is v naught t plus half at squared. Okay, and this is nothing but, so this is v squared. So now this is your famous third equation of 1D motion. It is only valid for 1D because you can't square vectors both sides like this directly. There will be a dot product between a and v naught. So that is a little bit different case there. But for 1D, you can write it directly like this, and this you can see from the second equation. It is x minus x naught. It is x minus x naught. It is written like this.
So sir, like for 3D we will do the dot product, right?
Yes.
Okay.
So for 3D, I can derive it in the sideways, but yes, you can always derive it on your own as well. So I'll just give you a glimpse. So this is your third equation, but the glimpse is for 3D. This is the equation v naught plus at, and you take dot product both sides with v vector. So it is v vector into dot v vector, and here is v naught plus at dot v naught plus at. Okay, and this becomes v naught square. This becomes v squared, a magnitude of v squared, of course. This is v naught squared plus a squared t squared plus 2 times t times v naught dot a. This is something that you will get as a third equation. There. Now you can, like, if you want, you can change something, but this is the third equation. Okay.